Hi Bob, I've been reviewing the quantum computing papers from July 2025, and there's quite a fascinating collection of work. I'm particularly intrigued by the breadth, everything from financial applications to quantum software engineering. What are your thoughts on the key developments this month?
Alice, you're absolutely right about the breadth. What strikes me most is how the field is maturing across multiple dimensions simultaneously. We're seeing practical applications like the financial risk assessment work with novel quantum circuit designs, but also critical infrastructure developments like Octopus, that open-source quantum computing stack. The combination suggests we're moving from pure research toward real-world deployment considerations.
That Octopus project really caught my attention too. Can you elaborate on why you think this kind of open-source infrastructure is so significant for the quantum computing field right now?
Octopus addresses a critical bottleneck in quantum computing adoption. Most quantum systems keep their operational software proprietary, creating huge barriers to entry and slowing standardization. By open-sourcing everything from cloud execution environments to system operation tools, it democratizes access to quantum computing development. This is particularly important because it includes transpilers, multiprogramming, and error mitigation, the nuts and bolts that system vendors rarely disclose. It's like having the Linux of quantum computing.
Speaking of practical applications, I was fascinated by the financial risk assessment paper. They claim to have solved the randomness problem in quantum circuits, which experts generally believe is impossible due to quantum computing's deterministic matrix operations. How do you interpret their approach?
That's a clever piece of work. They're using quantum superposition and entanglement to create pseudo-random distributions that are computationally indistinguishable from true randomness for their financial applications. Their random injection component leverages quantum parallelism to generate multiple random-like outcomes simultaneously, while their payoff computation component can directly identify values exceeding strike prices without classical preprocessing. The key insight is using quantum amplitude estimation to achieve quadratic speedup.
That makes sense. I also noticed several papers focusing on quantum software development tools and methodologies. The DECO-SE Quantum High-DE extension seems to be targeting the practical developer experience. How important do you think these development tools are for quantum computing adoption?
Development tools are absolutely crucial and often underappreciated. The DEQ-SE extension addresses a real pain point by unifying circuit design, code generation, and execution in a familiar environment like VS Code. What's particularly valuable is their support for iterative development. Quantum programming is fundamentally different from classical programming, and developers need tools that accommodate the experimental, probabilistic nature of quantum algorithms. The embedded quantum circuit simulator is also key for rapid prototyping without consuming expensive quantum hardware resources.
I noticed there are several papers dealing with quantum error correction and mitigation. The Krylov time reversal paper proposes avoiding controlled operations entirely. What's the significance of this approach?
The KTR approach is quite elegant. Controlled operations are notoriously difficult to implement with high fidelity on near-term quantum hardware. They require precise multi-qubit coordination and are highly susceptible to noise. By exploiting time reversal symmetry in Hamiltonian evolution, they can recover real-valued Krylov matrix elements using symmetric time dynamics. This significantly reduces circuit depth and makes the algorithm much more compatible with shallow quantum architectures. It's a beautiful example of using fundamental physics principles to work around hardware limitations.
There's also the adaptive windowed quantum phase estimation paper that seems to tackle similar NISQ-era challenges. How does their approach compare to the KTR method?
AWQPE takes a different but complementary approach. While KTR focuses on avoiding problematic gates entirely, AWQPE addresses the resource scaling problem of standard QPE by using small independent blocks of control qubits to estimate multiple phase bits simultaneously. The key innovation is their windowing approach combined with robust ambiguity resolution. This dramatically reduces the number of iterations needed. Both methods are targeting NISQ compatibility, but KTR is more about circuit depth reduction while AWQPE is about iteration efficiency. They could potentially be combined for even better performance.
I'm curious about the quantum software security papers. There are several addressing different aspects, from debugging quantum software to security in shared environments. What are the main challenges here?
Quantum software security is a fascinating emerging field with unique challenges. The debugging paper addresses a fundamental problem. How do you distinguish between bugs in your quantum code versus noise from the hardware? Their statistical approach using probabilistic metrics is clever, because quantum computation is inherently stochastic. The Shared Environment Security paper tackles a different but equally important issue. As quantum cloud providers explore multi-programming to improve hardware utilization, we need to understand the security implications. Quantum entanglement could potentially create information leakage between different users' programs running on the same hardware.
That security concern is quite sobering. Speaking of hardware utilization, I noticed the neutral atom quantum computer evaluation paper. What makes neutral atom systems particularly interesting for multi-tenant environments?
Neutral atom systems have some unique advantages for multi-tenancy. They offer flexible connectivity and can be reconfigured dynamically, which is perfect for running multiple simulations. However, the paper reveals that spatial co-location can increase crosstalk between concurrent simulations. Qubits that are physically close can interfere with each other. Their moving target defense strategy is quite innovative. By dynamically changing the spatial arrangement of qubits, they can mitigate crosstalk while still enabling safe co-location. This could be crucial for making quantum cloud computing economically viable.
I was also intrigued by the benchmarking studies. The Fujitsu digital annealer comparison on max-cut problems seems to provide some practical insights into current quantum annealing performance. What did you make of their findings?
That benchmarking study is quite comprehensive and realistic. They tested on graphs with up to 53,000 variables, focusing on wall clock time rather than just theoretical complexity, which is what really matters for practical applications. The finding that Fujitsu's digital annealer yields competitive results compared to D-Wave's hybrid system and other heuristics is significant. What's particularly valuable is their focus on performance statistics across over 2,000 graphs from MQLib. This kind of systematic benchmarking helps us understand where quantum annealing actually provides practical advantages today, not just theoretical ones.
There are several papers exploring the intersection of quantum computing with AI and machine learning. The LLM benchmarking for quantum operations caught my eye. Do you think AI will play a significant role in quantum algorithm development?
The LLM study is quite timely. They found that Gemini was fastest for generating quantum gate designs, with an 80% success rate across different LLMs. This suggests AI could indeed accelerate quantum algorithm development, especially for routine tasks like circuit synthesis. However, I think the real potential lies in hybrid approaches where AI handles pattern recognition and optimization, while quantum systems tackle the core computational problems. The key is that AI can help bridge the gap between theoretical quantum algorithms and practical implementations, automating the tedious parts so researchers can focus on the novel algorithmic insights.
The molecular dynamics simulation paper seems to highlight both the promise and current limitations of quantum hardware. What's your take on their benchmarking approach?
That paper provides a sobering but valuable reality check. They tackled fundamental quantum mechanics problems, free wave packet propagation, harmonic oscillator vibration, and barrier tunneling, and showed perfect agreement with classical methods on simulators. However, the results on actual quantum hardware from IBM and IonQ showed large discrepancies due to noise and hardware limitations. What's particularly valuable is their development of shallower quantum circuits for Gaussian wave packet preparation, which performed better on real hardware. This kind of benchmarking is essential for understanding the gap between theoretical quantum advantage and practical implementation.
I noticed several papers on post-quantum cryptography. The neural network-based digital signature scheme is particularly novel. How do you see the intersection of quantum computing threats and quantum-inspired solutions evolving?
That's a fascinating paradox, using quantum-inspired techniques to protect against quantum threats. The neural network signature scheme leverages the nonlinear relationships in neural networks, which are naturally quantum-like in their complexity. By using binary weights and a recurrent random vector that acts like an attention mechanism, they're creating computational problems that remain hard even for quantum computers. It's an elegant example of how understanding quantum computing can inspire new classical cryptographic approaches. The key insight is that not all problems become easy with quantum computers. We just need to find the right computational structures.
The fault-tolerant quantum computing architecture paper proposes using the smallest interesting color code. What makes this approach particularly appealing for early fault-tolerant systems?
The beauty of their approach is in the minimalism and practicality.
By using the smallest interesting color code, they're optimizing for near-term feasibility while still achieving universal computation. The key insight is using state teleportations between different error-detecting codes to access their respective transversal gates,
H gates for 2D codes, and CCZ gates for 3D codes. This means the optimization goal becomes minimizing quantum teleportation operations rather than non-Clifford gates. It's a clever architectural choice that could make fault-tolerant quantum computing accessible much sooner than traditional approaches.
I'm also interested in the quantum machine learning playground paper. How important do you think visualization tools are for advancing quantum computing education and adoption?
Visualization tools are absolutely critical and often overlooked. The quantum machine learning playground, inspired by TensorFlow Playground, addresses a real barrier to entry. Quantum computing concepts are notoriously abstract and counterintuitive. By providing interactive visualizations of quantum machine learning algorithms, particularly the data re-uploading universal quantum classifier, they're making these concepts tangible. This kind of educational infrastructure is essential for building the quantum workforce we'll need. Just as TensorFlow Playground helped democratize classical machine learning education, tools like this could do the same for quantum computing.
The encrypted state quantum compilation scheme addresses security concerns in quantum cloud computing. How significant is this threat, and does their solution adequately address it?
The ECQCO scheme addresses a real and underappreciated threat. When quantum compilation happens on the cloud side, user circuits are exposed to potential structural leakage and output predictability attacks. Their approach using quantum homomorphic encryption to conceal output states and quantum indistinguishability obfuscation to protect circuit topology is theoretically sound. The adaptive decoupling obfuscation algorithm is particularly clever. It suppresses idle errors while inserting obfuscation operations. With information theoretic security guarantees and only slight increases in circuit depth while maintaining high fidelity, it strikes a good balance between security and practicality.
The quantum unit testing paper presents an interesting methodology for validating quantum circuits. How does their approach compare to classical software testing paradigms?
Their quantum-centric testing approach is quite sophisticated. They compared traditional statistical tests with quantum-specific tests like the state vector test, swap test, and their novel inverse test across nearly 1.8 million mutated quantum circuits. The key finding is that quantum-centric tests, particularly state vector and inverse tests, significantly outperform statistical approaches in terms of precision and efficiency, reducing both false positives and negatives. This is crucial because quantum software testing can't just be classical testing applied to quantum systems. The probabilistic nature and quantum correlations require fundamentally different validation approaches.
There are several papers on quantum algorithms and optimization. The reinforcement learning approach for quantum circuit synthesis seems particularly innovative. What potential do you see in this direction?
A hybrid reward-driven RL framework for quantum circuit synthesis is quite promising. They're using tabular Q learning with a clever hybrid reward mechanism that combines domain-informed static rewards with dynamic penalties for inefficient structures. What's particularly smart is their focus on structured quantum algorithms with repeating operational blocks. This makes the exponential state space more manageable. Their results on Grover's algorithm, reducing gate counts while maintaining fidelity, suggest this could be a general approach for quantum circuit optimization. The key insight is that RL can explore the complex quantum state space more efficiently than traditional optimization methods.
I noticed the paper on quantum dark magic and intermediate non-stabilizerness. This seems to be getting at fundamental questions about quantum computational advantage. Can you explain the significance of their findings?
This is deep theoretical work that's crucial for understanding quantum advantage. The key insight is that while non-stabilizerness is necessary for quantum advantage, it's not sufficient. Even random states exhibit near maximal non-stabilizerness. They've developed tools to track how efficiently non-stabilizer resources are used across different algorithms. They're finding that structured approaches use non-stabilizerness more efficiently than unstructured variational methods, and that classical optimization freedom can lead to wasteful resource consumption, provides important guidance for algorithm design. It's helping us understand not just what makes quantum algorithms powerful, but how to design them to be maximally powerful.
The traveling salesperson problem benchmarking across different quantum hardware platforms provides interesting comparative insights. What did you find most surprising about their results?
What's most striking is how much the implementation process differs across hardware platforms. Neutral atoms, ion traps, superconducting qubits, and annealing devices each require fundamentally different approaches to the same problem. This highlights a crucial point.
quantum advantage isn't just about the algorithm, it's about the algorithm hardware co-design. Their comparative analysis shows that we're still in an era where understanding the specific strengths and limitations of each platform is essential. The fact that they had to develop different strategies for each platform suggests we're not yet at a point where quantum algorithms are truly hardware agnostic.
The differential topology paper on parameterized quantum circuits seems quite mathematical. How important is this theoretical foundation for practical quantum computing?
While it's highly mathematical, this work provides crucial theoretical foundations for understanding variational quantum algorithms. Expressivity, particularly dimensional expressivity, measures how well a quantum circuit can represent different quantum states, which directly impacts its ability to solve problems. By providing rigorous mathematical foundations, using differential topology and proving key statements about expressivity, they're giving us tools to systematically design better variational circuits. This kind of theoretical work often seems abstract, but it's essential for moving beyond trial-and-error approaches to principled quantum algorithm design.
I'm intrigued by the time-entangled quantum blockchain concept. How feasible do you think quantum blockchain implementations are with current or near-term technology?
The time-entangled quantum blockchain is conceptually fascinating but practically challenging. Their approach combining GHZ state blockchain features with quantum hypergraph blockchain scalability is theoretically sound, using phase encoding for classical data and achieving information theoretic security. However, the practical implementation faces significant hurdles, maintaining quantum coherence across distributed blockchain nodes, the fragility of entangled states, and the current limitations of quantum networking infrastructure. It's more of a forward-looking research direction that could become viable as quantum networking technology matures, particularly with advances in quantum repeaters and error correction.
The Scalable Modular Architecture paper proposes building quantum computers from smaller, controllable blocks. How does this compare to current approaches to scaling quantum systems?
This modular approach is quite elegant and practical. Instead of trying to build one massive quantum processor with full connectivity, they show that you can connect smaller, evolution operator controllable qubit arrays with just single entangling gates to create larger controllable systems. This significantly reduces the number of local controls and couplings needed. Their examples with 10 and 127 qubits, inspired by IBM processors, demonstrate real-world applicability. This approach could be crucial for scaling beyond current hardware limitations. It's much easier to engineer and control smaller modules with high fidelity than to maintain coherence across hundreds of qubits in a monolithic system.
Looking at all these papers together, what do you see as the most significant trends or themes emerging in quantum computing research this month?
I see three major themes converging. First, there's a strong push toward practical, near-term applications, from financial risk assessment to optimization problems, showing the field is moving beyond proof-of-concept demonstrations. Second, there's significant attention to infrastructure and tooling, development environments, testing frameworks, benchmarking methodologies, indicating the field is maturing into an engineering discipline. Third, there's a growing focus on hybrid approaches, quantum classical algorithms, AI-assisted quantum development, modular architectures, suggesting that pure quantum solutions may be less important than intelligent integration of quantum and classical resources. These trends suggest we're transitioning from the pure research phase to practical deployment considerations.
That's a great synthesis, Bob. It really does seem like July 2025 represents a maturation point for the field. The combination of theoretical advances, practical applications, and infrastructure development suggests quantum computing is becoming a real technology rather than just a research curiosity. Thanks for this insightful discussion. It's helped me understand the broader implications of these individual research contributions.